In this experiment, red, green and blue lasers attached to a travelling microscope are used to investigate the effects of atmospheric extinction. When light passes through our atmosphere, some of it is absorbed and some of it is scattered. The intensity of this light drops exponentially according to Beer's law. Here, I0 is our initial intensity, while I is the intensity after the light has travelled through a medium of thickness x. K, the extinction coefficient, is what you'll be determining in this experiment. In astronomy, information is collected from a variety of wavelengths, for example, ultraviolet, visible, infrared, and even radio waves. However, only certain wavelengths can pass through the atmosphere with little attenuation. The scattering from molecules and tiny particles less than approximately a wavelength of light is predominantly Rayleigh scattering, a form of elastic scattering when the photon energies are not altered in the process. Another form of elastic scattering is Mie scattering, which more predominantly occurs when the molecule has particle sizes larger than a wavelength. The main mechanism in this experiment is elastic Rayleigh scattering, which also occurs in space. The figure shown here is from the Pleiades cluster. In this case, the Pleiades stars are illuminating foreground dust. The blue appearance results from blue light being scattered more effectively by small dust particles. To perform this experiment, we made use of the following equipment. First, a Picotech Dr. DAC and Picoscope software, a vertical scale travelling microscope, a green, red and blue laser, a clamp or sleeve to attach the lasers to the microscope, and finally a Perspex tank filled with water and a small drop of milk. The milky water represents our artificial atmosphere, where milk fat globules act as an analogue to air molecules. The figure shown here displays the basic setup. To collect your data, we first filled the Perspex tank with water and then added a small amount of full cream milk. We then stirred the milk to ensure the fat globules were evenly distributed throughout the Perspex tank. A laser was then placed in a security sleeve and loaded into the barrel of the travelling microscope, which is currently in its lowest position possible. Under the Perspex tank, we placed the Picotech Dr. DAC, which includes an inbuilt photodiode. We then turned on the laser and adjusted the knob on the travelling microscope so that the barrel was raised in 5mm increments. We held each position for a few seconds to allow the Picoscope software to adequately record the light intensity level for each step. The process was completed until we reached the top of our artificial atmosphere. The entire process was then again completed for the other two lasers. In your provided worksheet, we provide you with all the data we collected, along with instructions on how you should complete your analysis. In addition to determining the extinction coefficient for the artificial atmosphere, you'll also be required to discuss a few other topics. Be sure to read them in full. If you have any questions, please email me. Otherwise, enjoy your practical.